Hey everybody, this video is about elastic deformation. So imagine you have some object like a bar. Okay, when you apply forces or torques to it, you could change the shape of the bar or deform it. Right, for example, you could apply forces like this, where you stretch it in tension, that's called tension, or other way around, you could smash it this way. Right, so that's compression. You could apply torques like this, and then the bar would bend. Or you could, say, like twist it like this, like wringing out a towel. That's torsion. You could like put it underwater, where there are forces from all different directions. So that's pressure. So let's just focus all of our attention this semester on one type, and then just know that your knowledge transfers to the other different types, which you'll go into more detail in future semesters. Okay, so let's just focus on forces that are along the axis of this bar, so axial to the bar. So two different possibilities, right? Compression or tension. Okay, so I'll just keep the drawing like this. And again, if the forces were like crooked like this, then you could decompose it. So then there would be a component along the axis of the bar, and then a component normal to that axis. But then again, right, that was shear. So let's just focus on the force that's kind of along the axis of the bar, which is perpendicular to this face, this area. I'll call this some area A. So that's the force perpendicular to this area. Okay, and then when you apply this tension, the bar would deform, it would stretch. So however much the bar, its original length, I'll call it L0 for its original length, it would change. Right, so there would be some change in length, delta L, some change in the length. Okay, so here are some definitions. Stress, I'll give it Greek letter sigma. Stress is this force divided by this area. Force over area. Okay, so then the units are newtons per square meter, but we name that after somebody. That's called Pascal. Right, just 1 Pascal. Right, just note that 1 Pascal is 1 Newton per square meter. Okay, so this is definition. Next definition, strain. I'm going to give it Greek letter epsilon. Strain is this change in length divided by the original length. Change in length divided by original length. So it's kind of a ratio, elongation ratio. So what are the units here? Meters over meters. So it's dimensionless. Practically, you could use percent. So you say, okay, the bar stretched by, the strain is, for example, like 0.01, or you could say 1%. Same thing, right? Okay, so we have these two definitions, and now one formula, which is Hooke's law, which is stress is proportional to strain. And this constant of proportionality is called the modulus of elasticity. And there are different types of stress, right? Like I was saying, tension, compression, you could bend, you could twist and torsion, etc. So there are all different types of stress, all different types of strain, all different types of modulus of elasticity, moduli of elasticity. So the one particular to this tension or compression along the axis, so for axial stress, then this would be called Young's modulus for axial stresses and axial strains. But I'm going to leave this kind of generic, so for whatever generic modulus of elasticity. Okay, so that's it. This was maybe another world's shortest lecture, right? So you have these two definitions and this one formula, Hooke's law. Oh, why is it called Hooke's law? Stress is like force over area, right? Strain is this elongation ratio. Let me move this area on this side of the equation. And then let me just rearrange this. Okay, so then it looks like this. Now, this whole thing is a constant, right? Modulus of elasticity depends on the material. That's the cross-sectional area. That's the original length. So the force is proportional to the change in length. Doesn't that look exactly like a spring, like Hooke's law? But now that spring constant, we're going into more detail. It depends on, it's not just one number, it depends on the material, the cross-section, and the original length. And it's not just for springs. Okay, and then just the detail. Elastic means if you stretch this bar, it goes back to its original length. That's elastic. If you stretch it and then it doesn't go back to its original length, it's like messed up forever, then that's plastic. So we'll go into detail in a future semester. Okay, let's try some examples here. So let's see, there's a rod. So it looks like, I'll just make some kind of illustration. Imagine there's a bar welded to the ceiling, and then it's holding a platform over here. And we know the mass is 550 kilograms. We know this original length of the rod is 2 meters. We know its cross-sectional area. Okay, and then what are we looking for? What is the stress and elongation, meaning the change in length? Okay, so what are all the formulas that you know? Stress, force over area. Strain is that elongation ratio. Hooke's law. Okay, so you know these three. Now, right, it's the same method you see me doing. Keep track of what you know and what you don't know. So let's check it out. Stress, we don't know. Strain, don't know. Okay, what else? Okay, this, we know it. It's mg, the weight of the platform. Area, got it. The change in length, we don't know, so this is unknown. The original length was 2 meters. Okay, so here we go. 3 equations, 3 unknowns. Right, which one do you want to solve first? Right here, solve for stress. Oh, let me go write a little more detail. So that is the weight, so mg. And then we know the numbers, right? 550 kilograms, we know g. What is the area right here? Just be careful. It's not meant to trick you, but 0.3 centimeters squared. Just be careful, because we want SI units, right? Meters squared. So how do you get from centimeter squared to meter squared? 100 centimeters is 1 meter. If you multiply these, that's not right. Right? You have to square it. Right? Then you have centimeter squared divided by centimeter squared, leaving you with meter squared. Okay, so just be careful when you do this kind of unit conversion. Okay, so here we got it. We got the stress. Take that number, put it right here. Okay, so take this, put it right there. That gets us mg over A equals E epsilon. I'll move the E down here. Okay, so then there we go. There's the strain. And then we take that and put it right there. Mg over A E equals delta L over L naught. I'll move the L naught over here. And there you go. This is the elongation. Oh, this modulus of elasticity is the Young's modulus right there. Okay, let's try another example. Okay, so, all right, so there's some kind of pillar. There's a pillar. And then there's a sculpture, some kind of sculpture. All right. And then, let's see, find the stress. Oh, 3 meters below, so over here. So here to here is 3 meters. Here to here is 6 meters. And then the strain. Okay. Stress, force over area. Strain is that elongation ratio. And then Hooke's law, stress is proportional to strain. Okay, what do we know and what do we not know? Okay, solve for stress. Okay, we don't know. We don't know. We don't know. We don't know. Okay, the cross-sectional area, got it, right here. The force acting at 3 meters below the top is how much? It's actually, so let's write this in a little more detail. It's the weight of the sculpture, which is 10,000 newtons, plus the weight of this amount of the pillar itself, right? So the pillar itself has weight. So how much does this weigh? So the weight of the pillar, how much is this? Okay, so we know that it has a density of 27, I'll just write over here, 2,700 kilograms per cubic meter. But how much cubic meters is this pillar? So the cross section is 0.2 meters squared, 0.2 meters squared, and is 3 meters high. So this is the volume, right? So density times volume gives us what? Kilograms. So that's mass. That's not weight yet, right? And then times G. So this is the weight of the pillar. Well, the top half of the pillar anyway. Okay, so now we got the stress. And then what should we do next? We can take that and plug it in right here and then get the strain. And then that's pretty much it, right? And we're done. We don't need this. And then what is the modulus of elasticity for granite? We just look it up. There you go. 4.5 times 10 to the 10 pascals. Got it. Right there. Okay. So practice a few of these problems and let me know if you have questions, and I'll see you in the next video.